So once everybody's in, Andrew, because I can normally not see, then let me know when I should start. Yeah, we're live, but let me know when you think I should start. Now? Okay, here we go. Hi, I'm Steffi Baum. I'm the Dean of Science here at the University of Manitoba, and I'm glad to welcome everybody to our interdisciplinary seminar talk by Dr. Karl Friston. We're pleased to have him join us from Great Britain tonight. Well, tonight for him, this afternoon for us, to speak to us. He was first invited by the Committee of Graduate Students for Scientific Interdisciplinary Talks here in Science to be part of our, what would have been our 50th anniversary celebration last fall. But due to COVID-19, everything got rescheduled, but we're delighted that it's worked out, and here virtually we'll get to hear him today. So I'm going to introduce him now and read about his many contributions and awards, and then we'll get to turn to his talk, which will be the highlight, I bet, a 40-minute talk followed by a 20-minute question and answer period, and then Emmanuel, our head of our graduate student committee, is going to say a few words. Don't be nervous, Manuel. Okay, so Karl Friston is a theoretical neuroscientist and authority on brain imaging. He invented statistical parametric mapping, voxel-based morphometry, and dynamic causal modeling. These contributions were motivated by schizophrenia research and theoretical studies of value learning, formulated as the disconnection hypothesis of schizophrenia. Friston currently works on the models of functional integration in the human brain and the principles that underlie neuronal interactions. His main contribution to theoretical neurobiology is a free energy principle for action and perception. Dr. Friston received the first Young Investigators Award in Human Brain Mapping in 1996, was elected a Fellow of the Academy of Medical Sciences in 1999. He was president of the International Organization of Human Brain Mapping in 2000. In 2003, was awarded the Minerva Golden Brain Award and elected a Fellow of the Royal Society in 2006. In 2008, he received a Medal College de France and an honorary doctorate from the University of York. In 2011, he became a Fellow of the Royal Society of Biology in 2012 and received the Weldon Memorial Prize and Medal in 2013 for contributions to mathematical biology. He was elected as a member of the EMBO Excellence in the Life Sciences in 2014 and Academia Europea in 2015. He's the 2016 recipient of the Charles Branch Award for Unparalleled Breakthroughs in Brain Research and the Glass Brain Award, a Lifetime Achievement Award in the field of human brain mapping. He holds honorary doctorates from the University of Zurich and Radboud University. And that's a pretty long list, but I think we're going to learn even more as we hand over the show to Dr. Friston. Thanks, Karl.
Well, thank you. It was a lovely introduction. Thank you. So, it's a great shame that I couldn't join you in person last year, but it's a real delight to be able to talk to you today, and it's a particular pleasure when one's invited by graduate students. So if you ever want to get somebody to speak at your institution, I think the trick is to get the youngsters to ask. So I have a few apologies. I tend to over talk, so I'm hoping that someone will stop me talking at about 40 or 45 minutes. The other apology is that I'm going to try and share with you some of my favorite ideas, but they are a bit dense and technical. So what follows, I think, can be taken as a sketch of the landscape and how everything fits together. And by everything, I am talking about first principle accounts of sentience, and in particular, the kind of mechanics that you can bring to the table to understand the way that we act, perceive, and indeed think. So this talk's going to have basically two parts. I'm going to tell the same story twice. First of all, I'm going to talk as if I was a physicist, trying to understand some of the fundamental principles of self-organization, what those principles mean in terms of dynamics, and in particular with a special focus on distinguishing things from other things using this notion of a Markov blanket. I'm going to close that session with a brief simulation to try and take the magic away and show the simplicity of some of the fundamentals of self-organization. And in the second half of the talk, I'm going to repeat exactly the same arguments, but using the rhetoric and the notions and the ideas that you'll be familiar with in the neurosciences and in psychology and behavioral sciences, but getting almost to exactly the same endpoint. So statistics of life will be the first part, and then a drilling down on the anatomy of inference from the point of view of neuroscience, closing with a consideration of the different kinds of actions that we can adopt, and a particular distinction between sort of reflexive quick actions and planning and thinking of the kind that we are extremely good at. So let me start this half with a question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, clearly, we're not going to be able to answer that question. What I want to do, though, is just focus on this notion of a boundary, which is absolutely essential if we want to distinguish something from something else or no thing. Schrödinger was the first person to acknowledge that the boundary was in and of itself a statistical construct. And I'm going to take that construct to be something called a Markov blanket, which I'm borrowing from Bayesian probability theory and causal theory. Some of you may know what a Markov blanket is. If you don't, I'll briefly take you through it. It's very simple. Imagine that the universe can be described in terms of a whole array of little states here denoted by these circles. And states cause states. So this state causes this state denoted by this little arrow here. And what I can do is I can identify the states internal to something, and by something I mean a particle or a person. And I'm going to denote those with a blue color and call them internal states. And the blanket states constitute the parents, the children, and the parents of the children, defined by these arrows or causal influences here. And the idea here is that this collection of blanket states here that surround the internal states contain all the information in the rest of the universe that will be necessary in order to predict what's going to happen on the inside here in the internal states. So technically, that means that the internal states are conditionally independent of the outside states given the Markov blanket. Everything I need to know is contained in the blanket states. So in a sense, these blanket states provide a veil or an insulation or a blanket that surrounds, say, my internal states. And everything I need to know about the rest of the universe is contained in those blanket states. I'm going to make a further move here. I'm going to split the blanket states into sensory states and active states, simply in virtue of the fact that the sensory states influence but are not influenced by the internal states. And similarly, the active states are influenced by, but are not influenced by the internal states, but are not influenced by the active states. So with this partition of different kinds of states that can constitute something, i.e. a particle or a person, I can start to talk about the internal states surrounded by blanket states that constitute the ensemble of states that constitute something. The reason I've done that should be more intuitive if we just look at some of our favorite examples of systems or things. So for example, the thing could be me or my brain, where the internal states would be all the synaptic activity and connectivity that constitutes the internal milieu of my brain. These internal states will influence, send signals to active states or action or actuators, my muscles, for example, or my autonomic reflexes that cause changes on the outside. The external states could be my body, it could be the external world outside my body. And then the external world, the external states, then generate sensations or sensory states in my sensory epithelia, which impinge and influence my internal states and so the cycle continues. And exactly the same dependency structure that enables me to separate the inside from the outside exists in anything. So for example, here there's a cell, and we can associate the intracellular states with the internal states that influence, say, the actin filaments that support or provide motility and push the sensory or surface states of the cell into the external milieu here, and then changes on the outside impinge upon the sensory states, the cell receptors on the surface of the cell that cause changes on the underlying, say, actin and the internal states. And again, we have this sort of vicarious circular causality where the inside influences the outside indirectly or vicariously through the blanket states here. And you can see here there's a mathematical image of the action perception cycle of a very elemental sort, certainly for a single-celled organism, but action and perception as more readily understood for more complicated and sophisticated systems like the brain. So what I want you to do now is forget about Markov blankets for the moment. What we're going to do is just do a brief crash course in physics, and then we're going to put the blanket states back in play and see what special properties of systems emerge. And the particular systems I'm interested in here are those systems that organize themselves in a coherent way so they last over long periods of time. Technically, those are known as non-equilibrium steady state systems, or systems that have attained non-equilibrium steady state. And all that means is that if I look at the system for a long period of time, it keeps revisiting particular states that characterize the kind of thing that it is. So I've sketched that out here in terms of two states, and you can imagine these lines here as describing the evolution of states as time progresses. And the key thing is, if I keep on following the course of the evolution of these states in this state space X here, I will come back eventually to a particular state that is characteristic of, say, me. This can be thought of in terms of a flow denoted by F, subject to random fluctuations denoted by omega. So this could operate at any time scale. It could be the fluctuations of cardiac states as my heart beats. It could be the very fast neuronal oscillations in a microcircuit in my brain, or it could be me getting up in the morning, having a cup of coffee, doing my emails, looking forward to lunch, and so on. Or it could be over a year, Christmas, Easter, summer holidays. The key thing is I keep returning to the same states. Technically, that means I have what's called a random dynamical attractor. Another way of interpreting this sort of cartoon of something here is that if you sampled me at random, the density of these flows also corresponds to the probability you'll find me in that state if sampled at any random time, which means I can describe this distribution of states, this attracting set, in terms of the evolution of its probability density, the probability of being in a particular state given I am me, for example. And I've written down the equation that describes the rate of change of this probability distribution here. It's called the Fokker-Planck equation. Don't worry about the maths. I just want to show you the overall architecture of the formalism that underwrites what I want to talk about when we return to Markov blankets. The way that we get to that in those important functional forms is, I've just said, I'm just interested in these probability distributions that don't change over long periods of time because they endure. And that just means that this is equal to 0. When that's equal to 0, that rate of change of probability distribution, that tells us something quite fundamental. It tells us that if I exist in the sense of attaining non-equilibrium steady state, then my flow must be a function of the log probability. So this functional form here, I'm going to unpack it intuitively in a second, but technically it just describes a gradient flow plus some circular or solenoidal flow here. So let me just show you what that means more intuitively. Imagine I placed a drop of ink in a glass of water. Now, normally, systems that don't attain non-equilibrium steady state would diffuse and dissipate, so that the ink molecules in this example would just keep on spreading away, flowing down concentration gradients to disperse throughout the solvent. But what I'm interested in, what we're interested in, are systems that persevere and retain their form and have an attracting set. So a magical solution of ink that gathers itself up again. So almost paradoxically, it looks as if it's flowing up concentration gradients in order to counter the dispersion due to, say, random molecular events that would otherwise dissipate the ink molecules throughout the solvent. And all that equation that I showed you previously is saying is that there must therefore exist a gradient flow that's flowing up the concentration gradients, up the probability towards those states that this ink, little globule of ink would occupy. And then there's something at right angles which has to flow around the isoprobability contours. And that's known as solenoidal flow. So all we're saying is that we can always write down anything that exists in terms of two kinds of flows, a gradient flow that gathers things together and stops them dispersing, and a circular solenoidal flow. And we're all familiar with that when we watch water flow down the bath hole. So let's go back to the Markov blanket. What I've just said holds for all states, which means that it holds for the internal states and active states. And in fact, it's easy to show that this gradient flow is a flow on the probability of the blanket states given a Markov blanket. And what I'm going to say is that this describes perception and this describes action. So my internal and active states are basically in the service of looking as if they are trying to increase the probability of my blanket states, or the kind of blanket states that I characteristically or characterize me, given me here. So you will all be familiar with this quantity, depending upon your background and your academic commitments and your favorite way of thinking about optimization and normative explanations for behavior. I put a few canonical objective functions here. So let's just start with the notion, well, of value. I mean, I've just said that this probability, the kinds of states that attract me are the ones that drive this gradient flow. So if I take the log of those probabilities, I've got a mathematical specification of those states that are valuable, the ones that I aspire to, the ones that I will be drawn towards. We can also write this down in terms of a negative free energy, which we'll come back to at the end. That perspective underwrites things like reinforcement learning, optimal control theory in engineering, and in economics, expected utility theory. This is nice because the negative of this value is known as self-information in information theory, which means also known as surprisal, or more simply surprise, which means we can also understand this sort of fundamental gradient flow, this fundamental behavior in terms of the principle of maximum mutual information, or the Informax principle in terms of minimum redundancy, and indeed the free energy principle as denoted by this F here. In turn, the time average of this surprisal or self-information is known as entropy, which means it looks as if this gradient flow is trying to counter entropic dispersion. And of course, this is the holy grail of theories of self-organization, in particular in synergetics and laser physics. And if you're a physiologist, it's just a statement of homeostasis, that we try to keep our physiological states within some bounds that characterize our physiology and are necessary for our enduring survival. I'm going to take another perspective on this quantity. So at the moment, I've been interpreting M as me, and then a Markov blanket that defines me. And I can also interpret me, or M, as a model of the outside states, so that I can now interpret this probability of the blanket states, and the sensory data, if you like, as the probability of some data given a model. And in Bayesian statistics, that's known as model evidence. And if you pursue that analogy, Then we have the Bayesian brain hypothesis that can be unpacked in terms of evidence accumulation. And what has become popular in the past few years is the notion of the brain as a predictive engine, a predictive coding device. And we'll cover that in the second half of the talk. Please don't worry about the equations. Again, I'm just trying to sketch for you the landscape and where what we're talking about fits in. And the key point I just want to make here, there's nothing special about this particular formulation of self-organization. It's just physics. And just to show you how that might work, if you're interested, we can derive from this gradient flow here all physics. So a few examples: if I suppress the amplitude of the random fluctuations denoted by gamma here, we end up with just the circular flow, the motion of heavenly bodies. And this is formally identical to Newton's laws of motion and classical Lagrangian mechanics. And at the other end, I can look at very, very hot, fast, small things where the gamma, the random fluctuations dominate, and we can ignore the solenoidal flow. And then we get to statistical thermodynamics and things like the fluctuation dissipation theorem and statistical mechanics. I can even deal not with the probability, but the square root of the probability, known as a wave function. And this equation is also known as Schrodinger's time-independent wave equation. And from that, we can derive all of quantum physics. So what we're talking about here is nothing special, apart from the fact we've got a Markov blanket in play. We've got this split between the internal and the external and the active and the sensory states. And in particular, we've just seen that the internal active states are performing a gradient flow on this one quantity, this value quantity, this sort of surprisal quantity or free energy quantity. I won't go into the details of this because I can give you a much better intuition in the next slide. But just for those people who are interested, that there are three key moves that the Markov blanket enables or allows us to make, which means that we can create a new calculus, a Bayesian mechanics, simply by applying standard physics in the setting of a Markov blanket. And those moves are basically just to note that the internal and the active states, which we could call autonomous states, share the same functional, this free energy functional here. It looks as though they're trying to always increase. And this functional does not depend upon the internal states. It just depends upon the blanket states. And crucially, it's a functional of beliefs about the external state. So functionalism is a function of a function. And I'm using beliefs in a sort of technical sense here, not propositional beliefs, but sort of posterior beliefs or conditional probability distributions, which is interesting because that, we'll see in a moment, leads to some philosophical implications. But let's leave that aside and just look at the simplicity of the argument that inherits just from the existence of these blanket states. Let's come back to our cartoon of a little universe. But now we're going to take a slice through this, say, probability distribution for one particular blanket state, one sensory state at this point in time. And just by eyeballing this probability distribution, you can see immediately there's going to be some mapping between the internal states and the external states, despite the fact that there's no direct coupling between them. And this mapping, I'm going to illustrate twice at the end of this part of the talk and the end of the next part of the talk in terms of a synchronization manifold here, which is just a fancy way of saying that what happens on the inside has to, in a probabilistic sense, map onto what's happening on the outside, despite the fact that there's no direct connection. And that's going to be basically the heart of the argument about how the inside infers what's going on the outside. We won't do that at the moment, but one can spin off all sorts of really interesting stories in terms of information geometry, given this statistical manifold. All we need to remember is that the internal states somehow parameterize probabilistic beliefs about external states. So let me just give you an example of that briefly before concluding with the second half of the talk. The example is going to use a simulated primordial soup. So what we've done here is just write down some flow, some equations of motion that describe 128 little macromolecules all jiggling around, exchanging with each other through local interactions, weak electrochemical and strong repulsion. So they're all jiggling around here. So I've created a little universe, and you may be asking, why have we done that? Well, what we can do is, because we have written down the equations of motion, we know exactly what influences what. And if we know that, we can now look for the Markov blanket that surrounds a small number of internal states and ask the question, is there a little synthetic creature living in this soup defined by its Markov blanket? And if there is, does its internal states seem to infer under this Bayesian mechanical interpretation, the Bayesian model evidence interpretation of the gradient flows that must be in play if this creature exists? And it's relatively easy to identify this Markov blanket in terms of the parents, the children, the parents of the children. I've done that here just by showing the simulation that we saw previously. But what I've done now is color-coded the little molecules according to whether they're internal states that are underneath or surrounded by the active states that support the sensory states in magenta, pushing them into the external states, which are in cyan here. And indeed, what we see is a little virus-like particle wriggling away with its cilium or tail here, sitting in this soup at non-equilibrium steady state. So now the question is, do the internal states infer anything about the external states? And again, it's almost inevitable that they have to. And here is an illustration of that. So what we've done here is ask, is there any mixture of internal blue states that is correlated with the motion of external states? So you can look at this if you're a cognitive scientist or neuroscientist, as asking the question, are there any electrochemical changes in the brain that respond to changes or in the motion of the, say, the visual world out there? And it's almost inevitable that you will find these things. So here's an example here where the prediction of the external motion, the flow of the external states, is given in dark blue, and the true value is in cyan, and these are the 90% confidence intervals. And what we see is the actual outside is indeed falling within the inferred range of motion based purely upon the internal states, despite the fact that these states are never directly exposed to the causal fluctuations in the external states. Just for those people who are familiar with event-related potentials in electrophysiology, what I've done here is just pick out the sort of extreme fluctuations or movements in the external states and superimpose and average them to show you what it would look like if I tried to create a synthetic or a simulated ERP subject study. And here are very similar results from monkey electrophysiology, showing you this coupling between the inside and the outside that is underwritten by this mapping, this manifold that undergirds the synchronization between the internal fluctuations and states and the external states. And I've used the word synchronization manifold here as a nod to a notion, again, I'm sure a lot of you are familiar with, which is the notion of generalized synchrony. So this is the observation by Christian Huygens that when two clocks are suspended from the same wall or the same beam, they will ultimately come to oscillate in synchrony. And that's basically what we're seeing here. So there's a reciprocal coupling, and here indeed is a drawing by Huygens here. So here's the beam, and here are two clocks. pendulum 1 and pendulum 2. And from our point of view, we can associate one clock with the internal states, and the external states are constituted by the second clock, and the blanket states are basically the beam that couples them together. Now, I like this drawing because it highlights a complete symmetry here. So if you subscribe to this formalism, this mechanics, where you're interpreting this self-organization, this gradient flow, as inferring what's going on out there in the world, then you're also committed to the notion that the world is actually trying to work out how you work and infer your dynamics, which is not a silly notion when it comes to things like eco-niche construction. However, let's just, we've done all the heavy lifting now. In summary, the existence of a particle, a person, priest, whatever, implies a partition of systemic states into internal blanket, namely sensory and active, and external states that are hidden from the point of view of the internal states from the internal states by the Markov blanket. And because active states change, but are not changed by external states, they reduce the entropy of blanket states, and this means that action will appear to maintain the structural and functional integrity of the Markov blanket. And in chemistry, that's known as self-assembly. In the life sciences, that's sometimes referred to as autopoiesis, self-creation. Internal states appear to infer the hidden causes of sensory states by increasing Bayesian model evidence, and actively influence those causes. And I'm going to refer to that in terms of active inference. This information geometry that I hinted at before leads us also to another notion that internal states parameterize probabilistic beliefs about external states, lending their expectations and information geometry. What that essentially does, if you're a philosopher, is it replaces a Cartesian dualism with a Markovian monism, but we won't worry about that. So a little bit of light relief here. I had a postdoc in London visiting, and en route to work in America, where he and his wife had a little baby, Kira, and he sent me this picture where Kira is proudly showing a Markov blanket that his wife bought their daughter. This is Markov here. So if you want a Markov blanket, you can get them in America. So there you have it. Right. Second half of the talk. I'm just going to rehearse what I've just said, but using a different kind of language, but with exactly the same fundamentals underneath it, talking about exactly the same mechanics, a calculus of belief updating that must be in play for anything that self-organizes to some attracting set or some characteristic states. And the idea here inherits from many great thinkers, probably from the students of Plato. It's the notion of this Bayesian brain as being a constructive organ, a fantastic organ, and literally fantastic in the sense that it's trying to generate fantasies or explanations, inferences for the causes of its sensations. And this is, I think, most elegantly illustrated by this oil painter from the 16th century, famed for doing still lifes, that when viewed from a different perspective, evoke a very different percept. So if previously you saw a bowl of fruit, and yet now you see a face, the key thing is that face is what you have brought to the table. This is something that you have generated from the inside out as an explanation for this particular pattern of sensory impressions, as opposed to something on the outside impressing itself on you from on an outside in kind of explanation, which might be a better way of describing how people thought about perception and the extraction of information in the 20th century. But nowadays, people have actually returned to 19th century understanding of this perceptual act by referring to the writings of people like Helmholtz, again beautifully illustrated by this sentence here. Objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. Again, this notion that you have to have something in mind as an explanation of the sensory impressions. And this is clearly something very closely related to Richard Gregory's hypothesis or explanation for perception as hypothesis testing, that you're just using the sensory information to confirm or disconfirm your best explanation for what is actually out there. And these ideas have been leveraged to great effect in many disciplines, in particular machine learning and statistics by people like Geoffrey Hinton, Peter Diane, borrowing formalisms based upon Bayesian probability theory, and in particular the work of people like Richard Feynman and his free energy formulation in quantum electrodynamics, basically to finesse and make the implicit Bayesian inversion problem tractable, coming up with the notion of the Helmholtz machine and subsequently the Bayesian brain. So let's just drill down on this producing the same impression on the nervous mechanism. So that's nice from our perspective, because we can imagine these impressions as shadows cast upon our sensory states, our sensory veil, the sensory part of our Markov blanket. And if it must be the case that existence implies this gradient flow that looks like inference, then we can interpret what's going on the inside as an attempt to explain what caused that. And in answering the question, well, how would you understand neuronal dynamics in terms of this gradient flow, neuronal flows of electrochemical states of the brain over multiple timescales, in terms of this self-organizing gradient flow that we did in the first half? The answer is actually much simpler than you might imagine. And I'll illustrate that just by writing down, here's our gradient flow again, here cast in terms of a gradient flow on this free energy functional, which stands in for this, this surprisal. And what we're saying is that the internal states change in a way to minimize free energy or maximize that Bayesian model evidence, sometimes known as self-evidencing. And I'm just rewriting this equation in terms of what an engineer would recognize as a Kalman filter with a prediction and update term here. If you are a more formal computational neuroscientist, you would know this as predictive coding. And it has two bits. It's what's going to happen next, given my expectations about states of the world, and an update or a correction based upon a prediction error, where the prediction error just is the gradients of the free energy. So what's a prediction error? Well, imagine I had this sensory impression, this sensory shadow here on my sensory epithelia, and I had some expectation, in this instance, that it was a dog that was producing these sensory impressions. And if I had a generative model that could generate from this expectation what I would see if this was true, I can then compare the prediction based upon my generative model with my actual sensations, my sensory states, to form a prediction error, which is just the mismatch between the two, which means that we can forget about the Schrodinger wave equation, forget about gradient flows. All we're saying is that everything that exists can be written down or understood as trying to minimize its prediction error. It doesn't mean to say you'll ever actually know what caused your sensations, but as long as you can keep your prediction error low, job done, that's good enough. So that provides a very simple account of action and perception. So if we're just trying to minimize our prediction error, there are two ways we can do that. We can either change our internal states to generate better predictions in the sense that they are closer to our sensations, and we can think of that in terms of perception, or we can resample the sensations actively by using our active states to make them more like the predictions, so that action and perception are working hand in hand to jointly minimize prediction error. And just for those people who are interested in the functional anatomy of this, the deep hierarchical structure of our brains in the service of minimizing this prediction error, I've just sketched out the kind of message passing we think is, or one explanation for the neural dynamics in cortical hierarchies in the brain. So if I asked you to build a generative model that maps from what's out there and where it is to actually generate the sensations, which would be my predictions that I need to form my prediction error, you'd have to start off with, what am I looking at? Where am I looking? How are my eyes moving? And then I could cascade through a very deep, i.e. with hierarchical depth and nonlinear and dynamic generative model, and ultimately work out what I would see in terms of foveal samples here. So I've written down the generative model mapping from these sort of hidden states, external states here, to generate my sensory states with these random fluctuations omega. And what's going on the inside is just that gradient flow that we've spoken about. And the architecture of that flow retains or inherits from the architecture, the way that the sensations were generated. Indeed, we can use that deep architecture to now understand neuronal message passing or neuronal dynamics in terms of no longer random fluctuations, but prediction errors that are sent forward to update up the hierarchy, to update my expectations. So I have a prediction here, it's generating a prediction error by comparison with my sensations, and that prediction error is driving my expectations to provide a better explanation in the sense of minimizing prediction error. And that's all that this equation is saying. And of course, this is happening level after level after level. Just to put a bit more flesh on that. So what we have in mind, literally in the brain, for neurodynamics is this counter stream of descending predictions that are always being finessed and improved through this process, sometimes known as Bayesian belief updating, by these ascending predictions that go deeper and deeper into the hierarchy and away from the sensory cortex. So here's a little example, and I'm calling it predictive coding with reflexes, and you'll see why in a second. Let's imagine that we had some visual information coming from the retina. It comes down to the a structure deep in the brain called the lateral geniculate nucleus, and it's in receipt of some top-down predictions from my visual brain here. And then that generates a prediction error that's sent forward to revise my expectations encoded by the neuroactivity of particular neuronal populations to make it a better prediction, so that the prediction error is slowly cancelled. But these states, these expectations themselves, are in receipt of top-down predictions. So we can compare these predictions or expectations with the predictions based upon higher order expectations to form a second order prediction error that then goes up and informs this and ultimately provides a deep internally consistent explanation of different levels of abstraction of the pattern of sensory inputs. Let's think about another kind of input for a second. Proprioceptive input coming from the stretch receptors in the oculomotor system controlling where I'm looking. These come in, they could be in receipt of top-down predictions, and I could generate and compute prediction error, say in the pontine nuclei, and we could use that prediction error to revise my expectations or Bayesian beliefs about where my eye is pointing. However, there's another simpler way that I can eliminate or reduce this prediction error, and that's through action. We can take this prediction error and feed it directly back to the muscles until they send the signals that I was predicting, and that eliminates my proprioceptive prediction error. That's exactly what we saw before in terms of applying this fundamental gradient flow to the active states. But if I was a physiologist, in particular a motor physiologist, what I've just described is just a classical reflex arc. And from that perspective, the descending predictions now provide a set point that enables the periphery, the reflex arc, to fulfill the predictions until the set point is reached and my eye is pointing where I predicted it to reach. So a really simple and biologically plausible realization of this dual minimization prediction error through internal states, our brain states, doing the belief updating, and then providing deeply informed predictions to generate a prediction error in the periphery, so in the spinal cord or the cranial nerves, that then actually cause me to move around. Or indeed, I could tell the same story in terms of autonomic reflexes. So I'm going to close now just by giving you a few examples using toy simulations of the sort of behavior that you can simulate using the principles and the gradient flows that I've just described. The first is an example that I like because it sort of can be unpacked to get right through to mirror neuron system like responses and action observation. But what we're basically saying here is that you can simulate quite sophisticated kinds of behavior just by equipping a synthetic brain with the right sort of generative model. Usually these generative models are very dynamic, and what I've done here is built a belief into this generative model that there is some abstract movement in some state space that can be mapped through a likelihood model or part of the model down to a point in some metric space out there that attracts my finger. So you can imagine that there's an invisible point in the world and it's pulling my finger around. And if I believe this is the way that the world works, then I will have predictions. I will be generating predictions, not only of what I will see, but also of what I will feel in terms of my muscles and my tendons being stretched. And if my reflexes fulfill those predictions, then I will actually move to generate what I predict I see, thereby minimizing prediction errors everywhere, multimodally in terms of descending proprioceptive predictions, eliciting prediction errors that resolve through action and movement, but also resolving visual prediction errors where the predictions in this instance can be thought of as corollary discharge. What would I see if I did that? And we can simulate quite sort of graceful handwriting-like behavior simply by configuring the mapping between these abstract points that define a central pattern generator to where we'd expect my finger to be pulled to. To get from just simply simulating action through to action observation, we can just look at what this would look like if I was an electrophysiologist recording cells high in the hierarchy where we have this belief about how the world is working and generating my sensations. What I've done here is just highlighted one neural population, say, and whenever its activity exceeds 1/2 of the maximum activity, I put a red dot at the point where the finger is. And what this shows is that it's very simple to generate things like place cell activity in the sense that this cell just fires when my finger is at a particular point. And furthermore, there's a directional selectivity here. It likes the downward strokes of the J and not the upward strokes. And the final move we can make is to actually just remove the descending predictions, attenuate them in the periphery, so that it's as if the agent can't feel what is actually being seen. However, this agent still has the capacity to predict what it would see if it were moving, even though it's not moving, or if someone else were moving. So here, what we've done is attenuate the proprioceptive prediction errors, just to show that exactly the same neural activity can be evoked when you're actually doing your own drawing, or when this agent is simulated to do its own action, as opposed to the visual replay of the same action in the absence of any motion. From the point of view of the generative model, if it just has to focus on explaining the visual input, nothing has really changed. It takes a slightly more time for the predictive machinery to catch up, but you see exactly the same phenomenology from a simulated electrophysiological perspective, showing that you get the same neuronal responses whether you're acting or whether you're observing that action, usually by another person. So that's an example of free energy minimization where the perception is driving, or it can be thought of as this gradient flow where sensations come in, they drive beliefs, expectations, in terms of to provide a belief about the external states, whilst at the same time the action is reflexively trying to minimize proprioceptive errors and doing the reflexes to make the predictions come true. So the last couple of slides are a different kind of action. At the moment, it's all about reflexes. We could tell this story for a person, but it would also equally apply to a virus. There's something quite special, though, about you and me in the sense that we plan. So I just wanted to situate one of the most interesting and challenging extensions of this formalism as an extension of this notion of action, but action in the future. So the idea here is that my active states are not just about quenching prediction errors or minimizing free energy in the moment. I can actually select actions. If my generative model had a temporal depth, if it reached out into the future, I could roll out the consequences of different courses of action and evaluate how much prediction error or free energy I expect to minimize if I pursue that course of action relative to that course of action. And then I can choose or select the actions or the policies that minimize the expected free energy. And when one writes that down, again, forgive the equations, but I think this is really interesting in terms of how it talks to other disciplines who try to understand what's good planning. Just technically, this free energy, in fact, any log evidence, is a mixture of accuracy and complexity. In machine learning, it's known as an evidence bound because it's always greater or lesser than the log of the what's called the log model evidence. Here is simply the probability of the sensory states here. I can rearrange this expression to evince Occam's principle in the sense that this evidence bound, or something that approximates model evidence, always maximizes accuracy under the constraint it's minimizing complexity. So you're trying to find the simplest explanation, the most evidence, the maximum evidence explanation is the most accurate one that is as simple as possible. If I now think about the consequences of action, I now no longer actually have data to accurately explain because the data have yet to be generated in the future. So I now have to take my the average under the outcomes that I think I'm going to see in the future to give us an expected free energy here called G. And in the same way that we can decompose free energy into accuracy and complexity, this actually unpacks in terms of risk and ambiguity. In other words, the risk of doing something is the expected complexity, and the ambiguity is the expected inaccuracy. So I just wanted to very briefly go through this perspective because I think it does highlight a nice connection with a lot of the formulations of good behavior, the kinds of behaviors that we aspire to, and they're all reflecting some aspect of this expected free energy. In the same way that risk is expected complexity and ambiguity is expected inaccuracy, the intrinsic value is the expected bound, and the extrinsic value is the expected log evidence here. So what do I mean by intrinsic value? Well, when one looks at this, you don't have to understand the maths, but I'll just tell you, what this quantity here scores is basically the amount of information I would get if I made that move. So in the visual search literature, that's known as Bayesian surprise. More generally, it's known as the mutual information between the causes, the external states, and the sensory consequences here, the mutual information that will be afforded by a particular action. I can make things slightly simpler and just remove one source of uncertainty. I'm going to do that by assuming that my sensory states, my external states are the same thing. I can see everything. I can sense everything. And then this quantity here actually reduces to something which is underwrites a lot of engineering and economics called risk-sensitive control. And all it's saying is that I'm going to choose those actions that bring my expected or anticipated states or sensory observations of the states into line with my prior beliefs about the kind of states that I should sample or experience or elicit. And in economics, I repeat, that's known as risk-sensitive control. I can take away uncertainty completely and just leave us with the extrinsic value, which we've already said can be interpreted in terms of expected value. And this is, of course, just expected utility theory in economics. So all of these different perspectives, if you like, are special cases of this general expected goodness of behavior, the G, the expected free energy, that enables us to plan and choose those behaviors that produce the minimum expected free energy. And just to close, I will illustrate that in the context of visual search, visual palpation, looking around the world or the visual scene in order to resolve my uncertainty, maximize information gain, responding to epistemic affordances. And I'm going to do that using the notion of salience maps. So, if I could only look at a small portion of this image, where would I look to resolve the most uncertainty about what I am looking at? So this is this intrinsic value, this Bayesian surprise, this information gain, this epistemic attractiveness or intrinsic affordance. And if I do that mathematically, I can work that out in terms of computing G here, and I can produce a little salience map, which actually very closely describes where people actually look. This from the classic work of Yarbus here. And I can simulate this. I can build a little generative model. We don't need to understand the details. All we need to know really is that this generative model, the synthetic subject, just has a very simple belief about the world. The world can be in three states. You can either be looking at an upright face, a sideways face, or an inverted face. And all that this subject has to do is to, synthetic subject has to do, is she has to just move around to resolve her uncertainty about whether it's like this, like that, or like that, responding to this information gain on this epistemic affordance here. And one can simulate very realistic visual saccades or sequences of how to data mine, palpate the visual world here. Here are the sequences of moves that are elicited. Here are the salience maps, which change, of course, because they're a function of what I now know, because you can't, the resolution of uncertainty depends very much upon what I already know about my lived world or immediate world. Here are the visual samples, and here is a graphical depiction of the resolution of uncertainty, both within and between making moves. So I'll give the last word back to Helmholtz, who's summarized everything that I've just said very elegantly in terms of each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we've understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. So all that remains is for me to thank those people whose ideas I've been talking about, and of course, thank you for your attention. Thank you very much indeed.
Okay, thank you very much for that and for taking the time to join us today and share your thought-provoking research perspectives with us. And while you've been speaking, a number of questions have been coming in on Slido. And so if you're willing to take those questions, we look forward to your thoughts on them. So if it's okay, Andrew, I've got a printed off copy. Well, I guess we'll just go with what's on the screen. So the first question is there a mathematical way to attribute a Markov blanket to a hurricane? Thank you for elaboration in this regard.
That's a great and difficult question to answer. It's almost as bad. Does a candle flame have a Markov blanket? Strictly speaking, no. So the things that normally people think about when they talk about Markov blankets, are physical surfaces, that surround a cell, or the sensory apparatus that we have available to us. The problem with hurricanes and Markov blankets is that, and candle flames, is that they exchange the states in a continual flux. So they are particularly difficult to handle mathematically. So if I was being mathematically precise, I'm afraid you can't. However, I would imagine in the next few years that there will be a formalism, probably based upon the Berkhoff's notion of wandering set, that does allow you to actually have a flux or a moving Markov blanket. Having said that, there are people, and the literature is just starting. There was a paper showing that the biosphere certainly can be treated as a Markov blanket, with some really interesting conditional independencies between sort of sun's irradiation and the temperature of the oceans and the like. So not hurricanes, biospheres.
Okay, thank you. All right, the next question: is there a way to estimate Markov blankets in situations where the environment is not fully observable?
Sorry, I'm thinking about that because, of course, to estimate a Markov blanket, I presume the answer is if one wanted to identify a Markov blanket, you would certainly need. Yes, it does not require the total environment to be observable. If you wanted to identify a Markov blanket and then make some inferences about what's going on the inside of the Markov blanket relative to what's going on the outside, it's only necessary, in virtue of the structure of the Markov blanket, just to identify those external states that impinge or affect the sensory states. I'm not quite sure I've got the essence of the question there. In a sense, the existence of a Markov blanket entails a kind of inference and estimation. So I'm assuming the question there was more about how you would associate a Markov blanket with a given system, say a cell or a community or a social structure.
Okay, thank you. I'm going to go off the grid here. How did you come up with this theory?
Oh, I thought I was going to have to do quantum versus not quantum. It's just the point of convergence of many decades of theoretical neurobiology that harvested what were clearly the right ways to formulate things, as I personally learned about both the physics and the psychology and the theory. So some of the key intellectual architects that I sort of appeal to, apart from obviously Helmholtz and Feynman, are people like Geoffrey Hinton and Richard Gregory on the perception side, and then you put into the mix your understanding of control theory from the point of view of the active side, and then it's just a question of trying to write down the obvious, which is basically action and perception are just in the service of the same thing, and just seeing where that can come from. So one nice thing about the free energy principle, as articulated in the first half of the talk, is that it conforms to its own principle. It just gets progressively simpler. I know it doesn't seem very simple, having watched that lecture, but I bet you in 3 years' time it'll be much simpler, because that's the whole point about minimizing complexity.
Okay, well, I think in the interest of time, because there's a lot of questions, you obviously drummed up a lot of enthusiasm with your presentation, and I want to thank you again, but we also want to have the opportunity for Emmanuel to say a few words, because I know he's extremely excited for the opportunity to welcome you. So I'll turn that over to Emmanuel, and thank you again.
Hello, Professor. That was a fantastic talk. First, let me thank you for joining us today. It is truly an honor. My name is Emmanuel Erwaju. You already know that. I'm a graduate student in the Department of Biological Sciences here at the University of Manitoba. I'm also the chair of COGSIT, an interdisciplinary committee comprised of graduate students from the Department of Microbiology, Chemistry, Mathematics, Statistics, Computer Science, Physics and Astronomy, and the Biological Sciences. We as a collective set the course to find a researcher, one whose work touched all our fields in a way that could dismantle the boundaries that have become barriers between scientific disciplines. Over several months, we searched for a researcher whose work could help establish a common language, a common way of thinking scientifically, a principled stance in which to seek an understanding of the hidden states of the world. Many researchers were proposed, but your work persisted. Not only because of the interdisciplinary nature of the free energy principle and its broad applicability across departments, it was not just due to your tireless efforts as a researcher, but also for your work's capacity to inspire others, to inspire students like me and my Markov blanket. So thank you for that, Professor Friston. And a special thanks to the Faculty of Science for supporting the ambitions of students. Cheers for that. Thank you.
Thank you.
Okay, well, again, thank you, Emmanuel. That was very nice. And a special thanks again to Dr. Friston for taking the time. It was really an excellent talk. We can't really say enough good things. That was great. And thank you, everybody, for joining us. Have a great weekend.